Alright, in this video we're going to work on some applied exponential problems. Specifically, half-life and compound interest. Now the first situation, half-life, this is kind of a simplified version of a chemistry problem, where you've got some sort of radioactive substance whose mass is undergoing exponential decay. And, if pretty much what's happening is that the rate of decay is proportional to the amount of substance left. And when that happens, what you've got is exponential decay. And so, set time intervals, you have half of the amount that you had before. And that's what we would call half-life. So the equation for this is A equals P times 1/2 to the T over H, where A represents the amount of stuff that's left, P is the starting amount, H is the half-life, and T is time. So really what's happening here is that, the starting amount and the half-life, these are quantities that are going to be given to you at the start of the problem, at least in this class. And then A is kind of the output of the function, and T is the input of the function, because the amount of radioactive substance that's left is depending on time. So let's look at an example. So suppose scientists find a 70-gram sample of a substance with a half-life of 2.5 years, and they're going to, run some kind of experiment on it. Okay, you might first be asked to write a formula that would give the amount of substance at time t years after they found the sample. So we start with the formula, which in this class will always be given to you, and we need to identify the parameters, the starting amount and the half-life. So this one's pretty direct. It's telling us, okay, they find a 70-gram sample, so the starting amount is equal to 70, and the half-life, which is h, that's going to equal 2.5. And so if we're writing a formula for the amount of substance left after t years, it's going to be a of t equals 70 times 1/2 to the t over 2.5. And now here are a couple questions we'll want to solve using the help of a calculator. So the first one's like, find the value of a of 10 and interpret its meaning in the context of the problem. So the calculator is going to help us with the value of a of 10, but it's not going to be able to help us with the meaning. So let's bring in a calculator. So for the first question, we're going to want to have a of t stored into y1. So we're going to say it's 70 multiplied by 1/2 to the power of t divided by 2.5. So x divided by 2.5. All right, and if we want to find the value of a of 10, we could go and we could just go out to the main menu and type in 70 times 1/2 to the 10 over 2.5. Right, we could do that. But we could also have the calculator do the work for us and to evaluate the function. So we can do that by calling on y1, the function that we just entered. And, it is an F4, but if you're not using one of the calculators that has the nice F menus, you have to get it out of the variables here. Y variables weren't in function mode, so we can choose that one, and that's where we get y1. And we can plug in y1 of 10, just like a of 10, and then get 4.375. And I'd say that value represents the A is the amount of substance that's left in grams after 10 years. And, the best response is definitely going to be citing the units there, but I think that's, really the big things with the units, that's something we can wait for calculus for. The value of A inverse of 10. Okay, this is something we did quite a bit in the last unit. Is finding the value of an inverse function. And so a inverse of 10, kind of what I told y'all to do, anytime you're confronted with that, you set a of t equal to 10. Like f inverse of 3, f of x equals 3. So a inverse of 10, a of t equals 10. And although this is the type of equation that we have learned how to solve in this class, we could solve this and get an exact value, we'd be limited to an answer that was like in terms of a log. And that wouldn't be the best thing ever. You might just like to know what number of years, maybe accurate to the third decimal place. And so we're going to solve this equation using the calculator. So we've already got, the kind of the left side of the equation stored in y1, right? So if we put in y2, 10, I think this is something that we've done a little bit in this course so far. we'd be able to solve the equation, right? If we could find an x value that made these two things equal, these two y values on the graph, then we would have a t value that made the equation in green true. Now when I go to graph this, I need to make sure that I've got 10 in my window. Y equals 10. And this is the standard window. And, I think this would probably work. But maybe I'll let y run up to 15 so that we can definitely see the intersection happening. And I'm going to hope for the best, right? Always start with a standard window or like slightly adjust it from the standard window. That looks like that's going to work, yeah. Now if we don't see the intersection, then we're going to have to manipulate the window until we do see the intersection. Okay, and we're going to solve this by going to calculate. Calculate the intersection. Between the first curve, which is blue, second curve is red. And if you don't have one of the colored ones, it's going to be like first curve is y1, second curve is y2. Give it a guess. There's only one intersection, so it doesn't really matter what the guess is. And then there it is. Okay, so the x value that made those two functions equal is 7.018, so the t value that's going to make these two things equal in my equation over here is going to be t equals 7.018. So I'm going to say a inverse of 10 is equal to 7.018. And since that's a t value, that represents seconds, and that can kind of like, help hint you towards the meaning of this in the context of the problem. A inverse of 10 is going to be the time it takes for there to be 10 grams of substance left. And honestly, for this class, this is really all you actually need to know is, like you working with making the formula, working with it, plugging in a value, solving an equation relating to that formula. For Algebra 2, that's going to be it. I'll show you where we could potentially go with this, though. The next level of questioning would be like, hey, at t equals 0, there are 125 grams of a sample of radioactive chemicals. At t equals 4, there's 40 grams left. What's the half-life? And I'll show you how I would do that real quick. I'd set up the formula, and then I would plug in a point that's related to the information they gave me at the start of the question. So I'd say, like 40 equals 125 times 1/2 to the 4 over h. And then I'd say, all right, I'm just going to have to solve this equation for h. Now again, if I wanted to do this, I'd have to use a log, and I'd only be able to get an exact value, and I wouldn't have really like a very good idea of what the value of h was. So I could bring in a calculator and solve this equation again by graphing. Figure out where 40 is equal to 125 times 1/2 to the 4 over h. Now again, I'm going to have to be careful because I need to equal 40, so I'm going to need the window to include y equals 40. So I might go from, 0 to 50. What's going on here? All right, 0 to 50, maybe with the step size 5. And, all right. Got this, and hopefully we've got some kind of curve coming through. There we go. And we're going to see where this intersects. So it's going to be calculate, what's going on here? Okay, not sure what that was. Calculate the intersection between blue and red. All right, what's going on here? Give it a guess. And then there gives me an intersection. So that'll be h equals 2.433. And that's going to be our main method for solving equations in this class. I know that this calculator actually has an equation solver, and a lot of calculators do, but a lot of them don't. And I've got students in my class that use a TI-83, and that one doesn't have an equation solver on it, and this is the most reliable way of solving an equation that everyone in my class is going to have. Now, the other situation we're going to be looking at here is compound interest. And so this is where you've got like some amount of money that's deposited at the bank. And at set intervals of time, they pay, interest to the account. So they, put in more money, and the account gets somewhat larger. Now, the key thing here is that the amount of interest they pay is proportional to the amount of money that's in the bank. And so that means that the rate of increase is proportional to the total amount that's already in there, and that's the hallmark of an exponential growth scenario. Now, the formula for this situation is going to be A equals P times 1 plus R over N to the NT power, where, like last time, A and T are the variables and P is the starting amount, but this time, we'll be having to contend with like the interest rate that the bank is paying, and that'll be R, and N, which is the number of times per year interest is added. And I think that it would actually, make the most sense to look at this formula with a specific example. So suppose $1,000 is deposited to an account at the bank that pays 4% per year, compounded twice per year. So like once every 6 months. And let's say, for imagination, that it's like once in the summer and once in the winter. So if at the start, you put in $1,000, and then, after 6 months, it paid you 4%, which would be $40, because 4% of 1,000 is 40. Added $40, and then we added, so then we'd be sitting at $1,040. Okay, and then we paid 4% of that. That'd be $41.60. Then we'd be sitting at $1,081.60, but that would be like 8% interest. So that's why they split up the 4% into two payments of 2%. So what we would be seeing is after 6 months, an increase of $20 of interest, and then after 6 more months, an interest of 2% of that, which would be $20.40. Okay, that would leave us with $1,040.40, and that would be more like 4% interest. Now, to try to reconcile that with the formula, what we've got, that'll always be given to you, is A equals P times 1 plus R over N to the NT power. And we're going to need to identify our parameters. Okay, the starting amount, that's the $1,000. The interest rate is 4% per year, so R equals 4%. And remember that 4% is 4 divided by 100, so that's 0.04. And that's compounded twice per year, so that means N equals 2. Because remember, N is the number of compounding periods per year. I don't know what keeps happening to my son. So for this example, our formula is going to be A of t equals 1,000 times 1 plus 0.04 divided by 2 to the 2t. And this should make sense, like with the, kind of situation we went through, where we were getting every 6 months 2%. That's this 0.04 divided by 2 that's 2%. And if we're multiplying by 1 plus 2%, really the 1 is what we already had, and that's going to stay in the account. And then the plus 2% is the interest that we're adding, and, proportional to the $1,000. And then the 2t is, if I went for 1 year, I would have gotten that payment twice, and we multiplied twice, and that was why we, had that slightly larger amount the second time, in the winter, where we got $20.40. Okay, so this is going to be the formula that we're going to work with. So the kind of questions I might ask you in an Algebra 2 class, outside of, write me a formula that represents this situation, is, what's going to be the value of the account after 3 years? And so that's kind of equivalent to asking, what's A of 3? And, if we plug in A of 3, plug in 3 wherever we see t, that would be 1,000 times 1 plus, and I know how to do 0.04 divided by 2, do that. 1 plus 0.02 to the 2 times 3 is 6. Okay, but I don't know how to take 1.02 to the 6th power. I guess I do, we could go and spend quite a bit of time doing the multiplication by hand, or we could bring in a calculator and have it do that work for us. So, I've added the formula for A of t into y1, and I'm interested in finding A of 3, so I'm going to go out to the main menu, and I'm going to call for y1, out of the variables menu, y variables, function mode, y1. You can also get this in F4, if you are, it's up, one of the green button menus. You can get it from F4 also. But we're going to call for y1 and plug in 3 and hit it $1,126.16. And if they asked us how long until the value is $1,500, we'd be solving the equation a of t equals 1500, and we could definitely go into the y equals menu and go down here and type in 1500, but then we'd really have to mess with the window a lot. And another option that we have is saying, if we're solving the equation a of t equals 1500, that would be the same as solving the equation a of t minus 1500 equals 0. And that's what we're going to do with the calculator so that we don't have to adjust the window. We're going to subtract 1500 here and hope that allows us to see the solution in the standard window, because the standard window always has y equals 0 in it, because that's the x-axis. So we're going to zoom to standard, and it might be like a close to vertical line, but hopefully we see it happen. Oh, but it's probably not. It's going to take more than 10 years. So let's give ourselves some more time. Maybe instead of looking from -10 to 10 years, it looks 0 to 20 years. And then I think this will be more likely to return us a solution. Yeah, there we go. All right, so this is a little bit more than 10 years, it looks like. And so it's still graphing, and we're going to calculate the 0. And okay, left bound t equals 10. Yeah, that looks right because y is -14. Right bound, we can scroll to the right a little bit. That's to the right of the 0. Give it a guess, and then that gives us t equals 10.238 years. All right, I think that's going to be all for this video. Really we're just dealing with some half-life and compound interest situations here, using the calculator to solve equations and find difficult to compute values. So, gonna work on these practice problems on that homework, and I think that should probably be good enough. That's all for this video. Thanks for watching.